Okay, welcome everyone. We are very happy to have Ankit Aggarwal with us today. He's going to tell us about near-extremal QFTs in 2D.
Not sure. Is this mic working? Great. So yeah, I would like to begin by thanking the String Group for inviting me here. This is my second time in ICTS, but first time in this campus. So I'm going to talk about some work that I've done with these people in the past few years and some ongoing work. And I'm going to talk about near-extremal quantum field theories in 2 dimensions. So yeah, let me begin by giving a sort of 5-line motivation / summary. So I'm going to go in more details, but to summarize, you might have heard that near-extremal black holes have a universal description in terms of at low energies in terms of JT gravity and Schwarzian theory. So at low energies, the dominant mode is just the Schwarzian mode. And one might wonder, what's the holographic dual of this statement? So what's the corresponding statement in the quantum field theory side? So that's sort of the big motivation. And I'm going to show that there is an analogous statement for certain quantum field theories in 2 dimensions. But the question about such field theories in higher dimensions is still open. Okay, let's first begin by discussing what are extremal and near-extremal black holes. So there are a couple of definitions. The first one is that extremal black holes have vanishing surface gravity at the horizon, or their temperature is 0. Another one is for a given mass, a black hole can have a maximum charge and angular momentum. And if you have charge and angular momentum that saturates or exceeds this bound, then the horizons disappear and naked singularities appear, which is in contradiction with cosmic censorship hypothesis. But when this bound is saturated, then the black hole is an extremal black hole. Usually these 2 definitions coincide. And whenever the bound is saturated, then you have 0 temperature. But in last few years, there have been some counterexamples that have been found, for example, by these people. And they considered Einstein-Maxwell theory coupled to a scalar field. And they showed that in such a theory, there are black holes which saturate this bound, like maximum charge and angular momentum for a given mass, but the temperature is not 0. But we won't be concerned with such counterexamples. For us, the extremal black holes would mean 0 temperature. Right. Right.
So in these examples, there are scalar
condensates. Yeah, there are hair. Yeah, they have scalar hair in the black hole. No, they are asymptotically flat. Yeah, I'm also not very familiar with the details of this paper. I just always mention it because when I first gave some similar talk, someone told me that there are these counterexamples. I mean, you can take Schwarzschild, for example, right? There's no angular momentum, no charge, but you have to take mass to 0. But I don't know any example where you have everything and non-zero mass and the bound is not saturated and the temperature is still 0. That I don't think.
This counterexample itself, that doesn't happen.
No, so what happens here is that the bound is saturated and the temperature is non-zero.
Black holes in this set, they're probably somewhere away from the bound.
Right, I would assume that they are actually at 0 mass. With non-zero mass, I think they. All right, so there are some very interesting universal features that extremal black holes show, irrespective of the dimensions or the theory. So they develop an infinitely long throat in the near horizon region. What this means is the dynamics of the near horizon region gets decoupled from the rest of the spacetime. Another way to say it is that the proper distance from the horizon to any point outside the horizon is infinite. And another feature is that the near horizon region of extremal black holes contain an ADS2 factor. This is true for a very large class of black holes. For example, this was partially shown in these two papers. And so this is very interesting and universal, but this is only true for extremal black holes. And in particular, this behavior does not survive when you add any finite energy to the system. So there are several ways to see this. One of them is to appreciate that the 2D gravity Lagrangian is purely topological. So when you vary the action, then you see that the stress energy tensor is identically zero, because it's topological term, you vary it, gives you zero. So the stress energy tensor vanishes. Another way to see it is that if you consider 2D dilaton gravity models, then if you turn on the stress energy tensor, then the dilaton diverges at near the boundary, and it completely destroys the ADS2 asymptotics. Yet another way to see this is if you go even slightly away from extremality, then the distance between the horizon and any point outside the horizon becomes finite. So the physics near the horizon is no longer decoupled from the rest of the spacetime. Right. So if this were the whole story, this would be very sad, because it would be just like studying the ground state of a quantum mechanical system without looking at any excitations. But however, it turns out that there is a universal description even when you go away from extremality, if you take into account the leading order effects of the back reaction of adding some finite energy excitation. And this effect of this back reaction is captured by adding this JT gravity action to the Einstein-Hilbert action. Again, for very generic near-extremal black holes. So back reaction of going away from extremality. Like if you, so for example, if you take this dilaton to be constant here, then this would describe an extremal black hole. But when you turn on the, so you turn on a small, slowly varying dilaton, and that would, so the whole, yeah, it does. Yes, so you see what's the effect on the metric because of this, essentially this JT gravity. Yeah, let me see if there's a better way to. So yeah, so for example, I said that, yeah, for example here. So if you turn on the stress energy tensor, then the dilaton would diverge near the boundary. So what you do is you incorporate this divergence into the action through this JT gravity action. I think that's what. So this term is sort of taking care of the back reaction, and whatever the new metric that you get, that would be because you have modified your action through this term.
You say leading order.
So that's the dilaton essentially. So it's the, yes. So you expand the dilaton. So you expand the dilaton as a constant plus something, which is not a constant. And this constant term is sort of the parameter in which you expand. It's, for generic black holes, this constant is related to the horizon radius.
You're saying
Yes. Yeah. Okay. And what you can do is you can compute the JT action on shell, and that is the well-known Schwarzian action. Oh, sorry, I forgot to say what are those. So this CJT is just a coupling constant, and in 2 dimensions. Phi is the dilaton, R is the 2D Ricci scalar, and L2 is the ADS2 radius. Now, yeah, so on shell, the JT action is given by the Schwarzian action. And this curly bracket just refers to the Schwarzian derivative. It's a 1-dimensional action. And C Schwarzian is related to the specific heat of the black hole. Yeah, this F tau is, it represents the reparameterizations of the boundary time of ADS2, where the ADS2 is given like this in the Pfefferman-Graham coordinates. And this action is also, it also famously captures the low energy dynamics of the SIK model. The interesting thing about this action is that it's exactly solvable, and one can compute the exact one loop partition function. And it's famously given by this prefactor with 3 halves, which comes from the 3 zero modes of SL2R, and this exponential. So this will be quite important in what we discuss, what we are going to discuss. Yeah, you can just compute the, you can just do the path integral. So these guys did it through some fermionic localization methods. So yeah, any questions until this point? Great. So now we are going to talk about the near-extremal quantum field theories. As I said in the beginning, so the goal is to understand what's the counterpart of the statement that very generic near-extremal black holes have this universal behavior described by JT gravity or Schwarzian theory. Yeah, so how does this universal description of near-extremal black holes manifest in the boundary theory? That's what we want to answer. So from holography, we know that if such a thing exists in the bulk, then there should be a regime of parameters in the boundary theory that describe the near-extremal black holes and reproduce their universal features described by the JT gravity or the Schwarzian theory. And we will refer to this regime of parameters in the dual field theory as the near-extremal regime of the quantum field theory, the dual quantum field theory. And it would turn out that the computation of quantities like partition function and correlation functions, it would be consistent with the Schwarzian theory. So one thing one can already guess is that this amounts to studying the thermal field theory near the 0 temperature, because the near-extremal black holes have temperature close to 0. And we would have to take further limits also. Yes. Yes, exactly. And Yeah, so we'll only look at QFTs in 2 dimensions, and we'll consider 3 different types of 2D QFTs. These are CFTs, 2D CFTs, warped CFTs, and Carrollian CFTs. A common characteristic of these theories is that they have a Virasoro factor in their symmetry algebra. And yeah, so let me just summarize what are the results for each of these QFTs. And yeah, then we'll go into more detail. So for 2D CFTs with large central charge, for a very large class of them, there exists a regime of parameters, namely low temperature and high angular momentum, where the partition function and correlation functions are determined by Schwarzian theory. This was shown in 2019 by Ghosh, Maxfield, and Toriachi. And these results are compatible with the bulk computations of near-extremal BTZ. One could do something very similar in the case of warped CFTs. No, yeah, you need a twist cap, and the theory has to be unitary and compact, but I will come to that. I'm just summarizing for now. Sorry? I mean, yeah, I guess you could, I guess you could define it this way. Like, yeah, I guess in this paper also they call it near-extremal CFT. But I mean, it's not a generally accepted definition, but yeah, I guess in this talk I will refer to this range of parameters as near-extremal CFT. It's sort of a very loose term. It's not a standard definition of near-extremal CFT. I'm just decided to call it that. I mean, you just take any CFT and you consider low temperature and large angular momentum, and that's sorted. Yeah, something very similar is also true for warped CFTs. So these are very similar to CFTs, but they have the symmetry algebra is a bit different. Instead of 2 copies of Virasoro, you have 1 Virasoro in semi-direct product with U1 Kac-Moody. And this is just the space-time symmetry. It's not internal U1. And here also one can show that for non-unitary warped CFTs, there's a regime of parameters where the partition function is determined by warped Schwarzian theory, and it matches the low energy behavior of complex SYK model. This is it's not as well known. It's essentially, I mean, for example, in the partition function, instead of 3 halves, you get a square. There are sort of 4 zero modes. Yeah, it's also one loop exactly. Yes, there is an extent description. I'm not going to discuss that, but yes, there is. So you should think of, you could define it on a circle, and instead of, I don't think I remember. So this was Hamid Afshar and some other people from Iran, I think. But yeah, I mean, in terms of partition function, it's very similar, except that there's a square instead of 3 halves. And
what is
the Schwarzian theory? So I think if you consider, in the action, you would have like JT action, but you would also have a gauge field, a U1 gauge field. So when you have that, so it's like SL2R times U1, that you kind of need to have that then this U1 provides you an extra zero mode that appears in this square structure. Yeah. No, it's called WOP because the algebra sort of matches the algebra of WOP CFTs. So it's the symmetry algebra is similar. Yes, if you take the complex SYK, low energy complex SYK, then the part yes. So there's a U1 mode. So that's and these results are also in line with the near-extremal limit of warp black holes. These are black holes in some three-dimensional topologically massive gravity theory, for example. Topologically massive gravity is Einstein-Hilbert action plus gravitational Chern-Simons term. So yeah, again, there's a match between. Yes, so essentially it's, so the symmetry algebra is Virasoro times U1 Kac-Moody in a semi-direct product.
That is true when you
yes, essentially.
So this comes with about
yes, exactly. So you can think of them as deforming ADS3 ADS3 space-time, and you add a warping factor, and then you get. So you can think of them as deforming ADS3 metric or deforming BTZ metric. There's warp BTZ and I can show it's in the metric, so it's essentially instead of d phi square, you have an extra, the prefactor has some warping factor. Yeah, so there is, I mean, you could have rotating, I mean, I can also show you probably the metric.
There is this thing of looking at the near horizon extremal.
Yes. So so if you consider extremal current and you go to near horizon region, that also has SL2R times U1 symmetries in this near horizon region. It's very similar to warp black holes. That's why people started studying these warp black holes, because they capture a lot of the properties of the near extremal curve black holes. That was the motivation, but these are exact solutions to topologically massive gravity. And this warping factor is related to the Chern-Simons coupling that so it's not a CFT, it's a warped CFT, and it has it has like negative norm states, like some of the descendants have negative norms, and so you could build such. I'm not sure if one knows any non-unitary examples. For unitary examples, for unitary theories, people have constructed them in 2 dimensions. For example, it's possible to consider it out of Weil fermions. We don't know non-unitary examples.
You're saying for large class of
so no, we know the formal properties. We don't have an action, for example. I don't think we know any.
There is like
yes, there is a well-defined representation. Yes, exactly. Yes, exactly. So there is the representation theory is well studied, but I don't think we know explicit examples. And we also know that all the holographic warped CFTs, they have to be non-unitary. All the examples that we know of holographic, so the theory dual to warped black holes is non-unitary. We know that because the level turns out to be negative and so on. So so a level of the algebra, the U1 gets. Doesn't it imply non-unitary? I think it implies non-unitary. No, to change the sign, you have to multiply with an I. You have to multiply I in the, so it appears in the commutator between P and P, right? So whatever, PM, PN. This is some, I don't know. No, so I mean the level appears in the K by 2 delta and then some P naught probably also. No. Yeah, these are the U1 generators. Yeah, yeah. So I mean, if you want to change the sign of K, you essentially have to multiply them with I. Hmm? Yes. Hmm? No, but this level is actually, I think, yeah, I'll have to look at it. But the point essentially is when you have this negative level, then when you compute the norms of the descendants, this plays a role, and then those become negative. If you have but okay, yeah, anyways, I'm not going to talk about warped CFTs in this talk, but yeah, maybe we can discuss it later because I just wanted to summarize some results. Yeah. All right, so yeah, so what we'll also do is, yeah, so we also showed that only non-unitary warped CFTs have this behavior which is governed by warped Schwarzian theory. So based on that, we conjectured that only non-unitary warped CFTs can have interesting holographic duals, because only these can have near-extremal black holes. And what we also did was to compute the exact modular S matrices of warped CFTs that can potentially be used to obtain the density of states of near-extremal warped CFTs, although we haven't been able to do so because of some technical obstructions. Great. So now we come to the third 2D QFT, which will be the main topic of the talk. So these Carrollian CFTs also seem to contain a near-extremal type of sector. Yes, yes. It says, and In this regime, the partition function is dominated by vacuum character, and it looks similar to Schwarzian partition function. And this is some work that will come out soon. However, we do not know what the interpretation of this is, because in the bulk, when you don't have a cosmological constant, there are no black holes. And if there are no black holes, then what does near-extremal mean? The bulk interpretation is not clear, but from the field theory side, we see some partition function which is similar to Schwarzian partition function. Although there are flat space cosmologies in the bulk, but they only have one horizon, so it's not clear what near-extremal or extremal means. And yeah, again, we find the exact modular S matrices of Carrollian CFTs, which can be used to derive the density of states in this near-extremal regime. And it looks similar to Schwarzian density of states. Great. So it's so
usually you have an expected kind of
right. So for example, in a CFT, you have if it is on a torus, then you have it's invariant under S transformations. And what you can, so you have characters, and the characters in the direct channel are related to the characters in the dual channel, the S transform channel, through modular S matrix. You can write the characters after the modular transformation in terms of the direct characters. And the object that relates the two is the modular S matrix.
basically you take the characters
Mhm.
and you take out going to minus one.
Yes.
Then it's a linear combination of
Yeah, exactly.
the linear transformation.
Yes. Yeah. Yeah, we in this paper
So you
we
get
derived.
modular form. Next modular form.
Yeah, exactly. Yeah.
Full modular.
Under full modular group, yes. The T matrices are trivial, kind of like they are simple. The S matrices are more complex. Yeah, if the time remains, I will also show them explicitly. So at least for the Carrollian CFTs. Yeah, in all these three cases, there is a universal regime, which is the Cardy regime, which was well known earlier also. So we'll try to also compare it to the Cardy regime, this near-extremal regime that we discussed. Great, let's first review near-extremal CFT. This is mostly based on the work of Hosch, Maxfield, and Toriaci. So let's consider a CFT2 on a torus with the modular parameter tau. And yeah, now the partition function is the usual partition function where this Q is related to some e to the power I tau and e to the power I tau bar. And L0 and L0 bar are the generators of the Virasoro. And this partition function is modular invariant. So the partition function before the modular transformation is same as the partition function after the modular transformation. And this partition function can be so further decomposed as sum over characters. What you can do is you can, sorry? Yeah, these are Virasoro. No, we are right now we are just talking about CFT2. So this trace you can further break down, and you can what you can do is you can trace over each primary separately, primary and its descendants. So you trace over each Verma module separately, and that's called a character. And then you sum over all the characters. So this is what you get. Where chi is a character, and this chi1 is the vacuum character, and these are all the other non-vacuum characters. Yeah, as I said, Q and Q bar are related to tau in this way. And Yeah, chi is just the trace over a single Verma module instead of the whole Hilbert space. H, yeah, is the weight of the primary. And beta left and beta right are the inverse left and right temperatures, which are related to tau and tau bar. In terms of beta left and beta right, yeah, I'm just writing the same thing in terms of beta left and beta right. So this should be V of H is again the same Verma module. And now it's easy to see that since the primary has the lowest eigenvalue of L naught, so when beta left or beta right is going to infinity, the term that dominates is the one which has lowest eigenvalue of L naught, which is the primary state. So all the descendants are suppressed by the Boltzmann factors. And however, to get this prefactor that I showed you of the Schwarzian partition function, this 3/2, you need the contribution of descendants. So what we would do is we would first do a modular transformation and then take this limit. That's why we'll now go to the modular transform channel. And in this channel, again, the partition function you write in terms of characters, but now these are characters of after the modular transformation. And you take the high right moving temperature, or beta r going to 0. What this does is this projects onto the vacuum, because for the vacuum H is 0 and all the others are suppressed by such exponentials which are very small, because beta r is going to 0. And here this H bar gap is the lowest H bar, which is other than the vacuum. So vacuum has H bar is equal to 0. So the first excited state, first excited primary above the vacuum. Yeah, so all the corrections are at least this much suppressed. And this is one of the assumptions that the only state with H bar is equal to 0 is the vacuum, which is the existence of the twist gap. So H bar is equal to 0 implies H is equal to 0, which is the vacuum. So essentially the vacuum character in this limit just becomes this exponential. And you can further take the high left moving temperature and you'll just get the Cardy formula. Because for the left moving character also you'll get the same result, except beta L will be there instead of beta R. And then you can take the logarithm and compute the entropy and you get the famous Cardy formula. Great. So now we don't want to obtain the Cardy formula. We want to get the Schwarzian partition function. So for that, what we need to take a slightly different limit. This is the near-extremal limit. First, we assume that the central charge is large in the theory. And then we again assume that, not assume, but we take the right moving temperature to be high as before. But now we take the left moving temperature to be small. And both scale with C in the following way. So what this taking high right moving temperature does is that it projects onto the vacuum, just like it did earlier. Right here also it projected onto the vacuum. But this low left moving temperature, what it does is that it allows you to see the contribution from the descendants. And this is easy to compute because we know the exact formula for the characters, and in particular for the vacuum character, which is just this. For a generic character, there would be an H here. But since it is a vacuum, then H is 0. And there's this 1 minus Q because we have to subtract some null states because the vacuum is annihilated by L minus 1. So that state you need to subtract, and that's why it's there. And eta tau is the Dedekind eta function, which computes which counts the descendants. It's because of the definition of eta, because eta has 1/24. Yeah. No. It's just because the vacuum is assumed to be SL2R invariant. So it's annihilated by L0, L minus 1, L plus 1. So you have to subtract all the null states which are L minus 1 acting on the vacuum. Yeah, so for a generic primary, it's not this L minus 1 does not annihilate a generic primary. So for generic primary, you would get an H here, and everything you would get except for this 1 minus Q. But now for vacuum, you need to, since there are these null states, you need to subtract them out. We will see. It's just coming. I'll show you. So if you don't take it, then you don't get the Schwarz partition. So to get no, that doesn't help. I'll show you. It will be clear in a minute. So yeah. So essentially, once you take this limit of beta L on this, it's easy to show that you get this partition function. And this 3/2, it comes from, so one factor comes from here when you expand it in this limit, and half comes from eta tau. So it becomes 3/2. And then in the exponent, this beta L comes from eta tau, and this 1 over beta L comes from this guy. So remember, we have to first do the modular transformation and then take this limit. So you have to do it for minus 1 over tau. Substitute minus 1 over tau instead of tau here, and then do the take the limit. But it's very easy to see that. This is beta L going to infinity. Because beta L is going to infinity.
Okay. Yeah, sorry.
Exactly. For this term, you need C going to infinity because beta L is scaling like C, and you have a C. So it's order 1 term. It's subleading compared to this, but it's order 1 term. And this is the term which contributes to the entropy. This one does not, because it's linear in beta L. So when you compute the entropy, it contributes to the energy, not the.
The first term, the
no, this does not contribute.
That's the
yes, exactly. Yeah.
And the next term is the Cardy.
Yeah.
Usually you have one or the other. But both of them take the other term. Then, or rather, other way to say is there many other terms.
No, there are no terms. This
no.
Just comes from. So do you?
You're saying you're
I'm just.
the vacuum character.
Yes. So.
I assume the vacuum character is the term.
No. So exactly. That's what we got after taking beta R to 0. This was this argument. So once you take beta R to 0, then
the assumption is that there is nothing with H comma 0.
Exactly. Yes.
So it has a gap.
Exactly. So yeah, this is the assumption. Once you make this assumption, then taking beta R to 0 essentially projects you onto the vacuum in the dual channel.
Saying this thing.
No, it's very easy to do also. Actually, it's just yeah, it's it's just this eta tau behaves like an exponent for large tau, and that gives you this. Yeah, that gives you this one, and this one comes from the Q. There's just nothing else. Yeah, so sorry, this I wrote without S transform, but you have to first do the S transform. And the S transform of eta can be written in terms of eta. There's square root I minus I tau times eta tau. It's also a nice modular object, eta. You use that property, and then the square root I tau essentially gives you the half of this 3 halves.
It's not like square root.
No.
What are the subleading terms?
Yeah. Good question. So I'll have to remember because I didn't write them down here. I think there are, let me see. So yeah, so this 1 over beta L, this is coming from this guy. Let's see. What did I ignore here? I actually did not ignore anything. This is what I ignored here is maybe. No. So yeah. So for the Dedekind eta, that contributed this beta L over. So you're asking what's the subleading correction to the Dedekind eta is. It's exponentially suppressed. So the second term is exponentially suppressed compared to the first one. So I would guess that I will have to. This one. Yeah, so there, when you expand this guy, there would be, yes, the coefficient has polynomial correction, that's correct. But in the exponent, I think I might even have them somewhere, but I'm not sure if I would be. I mean, you can try to just do it on the board if you want.
First term in exponent is going to be.
Yes.
You're saying that the second term, you're about exceeding.
Yeah.
You have a term which is actually, like sometimes goes increasing, and the subleading term is also good. Until you get to the order one. Very surprising that only one term which goes increasing.
So what would you expect? You expect something like square root beta or something like that?
You're saying that's not there.
Yeah, it's not there, yeah.
I understand the leading growth is.
But you think that there might be terms which are so anything that comes with the so this term is essentially exactly coming from this guy. So the only worrisome thing could be here, where you expand eta tau. So the first one will be this. The second one, you are worried that it might be like 1 exponential of 1 or something. Even if it is there, then also it doesn't matter qualitatively, right? Like
the power loss that comes
so yeah. In the yeah. Sorry. So you are saying that the polynomial corrections here would enter in the exponent? Right, but Right. So, but the log term would be small compared to the order one term, right? Yeah, that's true. But that would be, subleading to this term, right? That term would be, so suppose you had this plus something, that would be,
But it won't be more than the term.
not sure. I think we did it. They did it, and then, that is true. No, that is true. But I'm pretty sure that it doesn't ruin the behavior. And I even have the orders and stuff in the paper. Like we read it their thing, and there's nothing to be worried about. But I mean, if you want, I can look at the paper and tell you. But yeah, I think it's. Anyways, okay, yeah, let's maybe go ahead and then I'll show you maybe after the talk. Yeah, so this is essentially the Schwarzian partition function. This, if beta twiddle is associated with beta L over C, and yeah, you just ignore this Casimir energy term. No, not ignore. I mean, I'm just saying that this is essentially proportional to Schwarzian partition function. You take it this times e to the power beta L over 24. So the partition, so this is a statement, right? So we have shown that if you, in this regime, the partition function essentially behaves like the Schwarzian partition function times something, right? Which something is exponential beta L over 24. Which, I agree, but this term doesn't contribute to the entropy.
That's not what you're saying.
Yeah, it's.
But the entropy looks like, are you saying the entropy looks like Gaussian or the partition? Have like a big number of.
Yes.
Not according to.
Yes.
So which is the thing?
So what I'm saying is the CFT2 partition function in this regime of parameters is proportional to the Schwarzian partition function. And the proportionality constant is large, I agree, but it's still proportional to this one. And this is the term that contains all the interesting physics. The large term essentially contains the physics that is also there for extremal black holes. This is the term that captures the physics of going away from extremality. So you could essentially write if you want to write the full partition function, then you would write it e to the power s naught minus beta e naught, and then this z Schwarzian. That's the more correct statement. I did not write the full thing. And yeah, so this is the term that's essentially beta L over 24. And there is also contribution. I just showed you the contribution coming from the left characters. There's also contribution from the right characters, right? That also I did not show explicitly, but that would also be contained in this e to the s naught minus beta naught. So there would also be this guy multiplying the left character, right? But yeah, this is again, yeah, it's just there. Which will, yes, this is going as c squared, yes. Yes.
There's a linear. Saying is.
So there is what? Yeah. Yeah.
So, the non-trivial statement is that is just convert by the conformity.
What is yeah.
Closely dealing. But there's a P factor.
Yeah.
But the P factor which comes from state because
So some of it is coming. So so out of the 3 1/2s, 2 of them are coming from this 1 minus q. And one of them is coming from eta tau, because when you do eta of minus 1 over tau is square root of minus I tau. The square root of tau, that gives half of them. So yeah, it's not just coming from the, yeah. Yes, exactly. And I will also, I think I would also discuss why this is exactly the limit you're kind of taking on in the bulk also when you're talking about near-extremal BTZ, for example. I think I will discuss it. Yeah, I'm going to discuss it. So yeah. Another point to note is that one essentially gets the Cardy entropy, but we also get some interesting log corrections. And these become important when you go to low temperatures because they contribute negatively to the entropy, and they essentially, as you go to extremality, they essentially take the entropy to 0. Yeah, so the assumptions in all of this were the following. We assumed that the theory was unitary, so H and H bar were positive. It was compact, so there was a unique vacuum, H is equal to H bar is equal to 0, and it was SL2R invariant. And there's a twist gap. That means that only vacuum has H bar is equal to 0. In other words, there are no additional symmetries. Okay, so next, let's see what's the bulk interpretation of this limit. And we'll find out it's essentially the near-extremal limit one takes in the bulk. By the way, did I answer your question? So C, you need to take C large because you want this term to exist. If you don't take it to be large, then beta L is large, and then this essentially goes to 0. We want to keep this term. Yeah. No, it's no, yeah, these are very important at low temperatures, these log corrections. But I'm saying that, so if you compute the entropy of this partition function that we obtained, then you get the Cardy entropy plus the log corrections, and these log corrections they are going to be large for small temperatures. But yeah, that's all I meant. Like this is Cardy entropy plus some log corrections, which may not be just the corrections, which may be the dominant piece. So I shouldn't probably use corrections. Yeah. Yes, that's correct. Exactly. Yeah. So that's what takes the entropy to 0 at low temperatures, and that sort of resolves the puzzle that people had. So C to infinity is like you take. Yeah, so you start with the CFT with large central charge, right? That's what you begin with. Then I think it doesn't matter in which order you take the limits, but just to be safe, let's say first you take beta R to 0, so large right moving temperature. That projects you onto the vacuum. And then you take large beta left, so small left moving temperature. And that gives you essentially the partition function, the Schwarzian partition function in the left moving sector. Yeah. So that would just what you could do, for example, here is do the Legendre transform twice. So you exchange this beta L and beta R for energy and angular momentum, and then you essentially get the Schwarzian density of states. Yeah, I think that's true. Yeah, it doesn't. That's true. That's true. I think it's not necessary that you need to do this. There's more freedom in choosing beta R. That's what they write in this paper, but we did point it out in our paper that it can be larger than, like it can go faster to 0 than this. So there is some, yeah. Yeah, so let's talk about the bulk interpretation of this limit. So let's consider Euclidean BTZ with the following identifications on the boundary. The Euclidean time is identified with periodicity beta and some twist theta. Beta is the inverse temperature and theta is the angular potential, and there is the usual 2 pi periodicity of the angular coordinate. And we define beta left as beta minus I theta and beta right as beta plus I theta. And now one can write a grand canonical partition function the usual way. And to go from energy and angular momentum to L0 and L0 bar, we use the following relations, and we essentially get the same partition function that we were discussing in the CFT. I just rewrote it in the same variables as CFT. Nothing very deep here. Now we'll try to see what the limits that we were taking mean in the bulk. So we know that, as we discussed, for the near-extremal black holes, the temperature is very small. So beta is very large. And we also want these near-extremal black holes to dominate the partition function. So they should be the leading saddle. For that, what we need is this condition. This is the condition for Hawking phase transition. So here, beta L times beta R should be less than 2 pi square. That's when the black hole will dominate instead of the thermal radius. And if you combine this condition with this condition, you essentially get this condition. Beta plus I theta is much, much less than that. And yes, theta is imaginary, purely imaginary. And yeah, near extremality m is close to j. This is the same as this condition essentially. So we basically get the same conditions that we were using in the beta minus I theta is very, very large, yes. So from the bulk also we get the same conditions that we were using in the CFT. They're both compatible. And yeah, you can write this condition in terms of charges also. It's the same. Great. So to again reiterate the same thing pictorially, we want to stay inside this hyperbola for the black hole to dominate the partition function. But we also want to approach extremality because we are interested in near-extremal black holes. So what you can do is you can stay inside the hyperbola and you can asymptote to this line, which is m is equal to j. And that's what you should do in order to for the black hole to dominate, as well as u being near extremality. So this is essentially what the limit did that we took on the CFT. Great. So let me summarize. So we took the partition function of a 2D CFT We wrote it in terms of characters, and each character holomorphically factorized in terms of a character depending on tau and tau bar. And then we did a modular S transformation and took large right moving temperature. This implied that the vacuum character dominated the partition function. And to get the Schwarzian, we took a small left moving temperature. And then the Schwarzian partition function appeared in the left vacuum character. One can also generalize this to other theories with which have some similar properties. And this is what we are going to do for warped and Carrollian CFTs. Let me just describe the generic procedure we are going to follow. So you consider partition function of a modular invariant / covariant QFT in 2D in our case. And then you write the partition function in terms of characters. And okay, there should be a sum here. And each character doesn't really, this property you don't really need, but we will have this property for the theories that we consider. So what you first do is you take, so there are these, again, two chemical potentials, tau P and tau Q, and PQ label the, let's say, the primaries. So you take tau Q to 0, you project onto the vacuum, and then once the vacuum character dominates the partition function, you already have some universal results, because then the results don't depend on the spectrum of the theory. They only depend on the generic properties of the vacuum. Like for CFT, it was SL2R invariance of the vacuum. So both warped CFT and Carrollian CFTs have this property. They are warped CFTs are modular covariant. There's some anomaly contribution, but so yeah, yes, one copy, not two. But and there are yeah, so maybe the statement is no. I mean, yeah, maybe I shouldn't say QFT, but what I'm trying to say is like this is sort of the general procedure that would work for both of the theories that we would consider. It wouldn't work for a generic QFT. So I don't know what you need to do for a generic QFT. Yeah, I mean, not in this way, but I think there might be a way to make it work there when you have currents in a CFT, for example. There might even be papers on that. So I think there is. Sorry, just a second. Sorry. Yes, that. Yeah, that's right. But that's for simplicity. I think that's assumption one might be able to relax. But yeah, for now we assume that. Yes. Right. And yeah, and once you take the
this character.
I mean, this need not be Virasoro characters, right? It could, in general, I mean, for us, it would be some Virasoro, Katzmodi, or some other kind of characters, but yeah. Yeah, probably true. Okay, and then one takes an appropriate limit on tau P, and we will see that we get a Schwarzian-like or near-extremal partition function. Okay, so now we'll jump to Carrollian CFT2 and near-extremal limits of these theories. Let me first. Yeah, so any CFT. Yeah, so the claim is any CFT which is unitary compact with a twist cap, large central charge has. Mm. Yeah, one needs to be able to project onto the vacuum, otherwise you won't be. And if you don't have the twist cap, then at least this way you can't project onto the vacuum, right? Because we had to assume that only state with h bar is equal to 0 is the vacuum. That's when. So. I'm not familiar with them. So do they have twist cap or not? It doesn't have to be large. It just has to be there. Like it can be anything because you can take beta r to be arbitrarily large. That doesn't matter. It just has to be there. It shouldn't be like continuous.
What a large twist gap.
Yeah, exactly. Yeah. Okay, so we'll first talk about what are Carroll theories. So these are the first, let's say, what are the Carroll symmetries. These are the symmetries that arise as the speed of light going to zero limit of the Poincare symmetries. These make space absolute and time relative, in contrast to Galilean symmetries, which make time absolute and space relative. These were first found by these people in the 60s, but they only recently become relevant when people found out that these are related to BMS symmetries. Essentially, these are essentially the same as BMS symmetries. And these symmetries are associated to null hypersurfaces, and thus they are relevant for flat space holography. And they have also found applications in condensed matter systems, like some fracton models, and for highly boosted fluids, tensile strings, and near horizon symmetries, where one also deals with null hypersurfaces. So these symmetries arise on a Carroll manifold, which is defined by a degenerate metric, h mu nu, and a time-like vector, which is in the kernel of h mu nu. So h mu nu tau mu is 0. And the Carroll algebra is generated by the isometries of this Carroll structure. The Lie derivative of tau mu and h mu nu is 0. That would be one of the isometries. Now, for d-dimensional flat Carroll spacetimes, you could choose a coordinate system where tau mu is dou t and the spatial metric is just the flat metric. Then the conformal Carroll algebra is obtained when you consider the symmetries which transform tau mu with weight 1 and h mu nu with weight 2. And this was shown by Duval, Gibbons, and Haworthy in 2014 that this algebra in d dimension is isomorphic to d plus 1 dimensional BMS algebra, which is the algebra of d plus 1 dimensional asymptotically flat spacetimes. And that's when the field really, people become really interested in these, because these can be now seen as the theories which have these symmetries can be seen as the boundary theories to asymptotically flat spacetimes. Great. So in this talk, we'll be interested in d is equal to 2 or BMS 3 or conformal Carroll 2. It consists of semi-direct sum of Virasoro and abelian algebra, and in the algebra can be written in the following way. It's the usual Virasoro algebra, and Yeah, it's a bit weird. There should be 1 over 12, but people have used it in the past, so we kept using it. But yeah, there's no deep reason. It's just yeah. So this is the usual Virasoro algebra, and then there are some mixed commutators. There's another central extension CM, and it's just the U1 algebra. So LNs are the super rotations, MNs are the super translations, the BMS language. And L0L plus minus 1, M0M plus minus 1, they form ISL2R algebra, which are the isometries of the 3D Minkowski spacetime. For Einstein gravity, CL is 0 and CM is not equal to 0. If you want to generate CL, then you need to pick a theory which has gravitational anomaly like topologically massive gravity, and consider, yeah, without a cosmological constant. Yeah, so as I said, the 2D QFTs with these symmetries are called Carrollian CFT2, and these are natural holographic duals to 3D asymptotically flat gravity. Right. So let's look at the partition function and modular transformations in these theories. So the partition function is defined in very similar way to CFT, where beta car is the inverse Carroll temperature and theta car is the Carroll angular potential. H is the same as M naught and J is same as L naught, where M naught and L naught were the generators that we saw here. M is equal to 0 and L is equal to 0. Yeah. So these theories can be obtained as a limit of Lorentzian CFT2. You need to take the speed of light going to 0. And for so you do essentially this procedure. You take time to epsilon t. You keep the phi as it is, and epsilon is taken to 0. For the generators, you do an Inoue-Wigner contraction. You define an ln through the Virasoro generators in the following way, just the angular momentum, and mn as the Hamiltonian, but with an epsilon factor, which is going to 0. And the left central charge is, CL is C minus C bar, and CM is C plus C bar with an epsilon factor again. Yeah, if you are starting with a unitary CFT, this guy would be 0 because C is equal to C bar, and this would be non-zero. That's why for Einstein gravity, CM is non-zero and CL is 0. Beta CFT is same as beta car, and theta CFT is same as theta car up to this epsilon. So there's some limit which you can apply to a CFT partition function, and you'll get this Carrollian partition function. And if you apply this limiting procedure to the modular transformations of a 2D CFT, you start with the usual PSL2Z, and you identify this tau, the beta car and theta car in certain way with tau, and you expand in epsilon. So what you get is tau is essentially sigma plus epsilon rho, where sigma and rho are related to beta car and theta car that we saw earlier. Under modular transformations, these would, using this rule, would go to this guy, and we are keeping only order epsilon terms in the expansion. So from this equation, we see that sigma transforms like the usual, like tau, but rho transforms as the imaginary part of tau. So that's the interesting change from CFT2, but it just comes from the expansion. A way to think about this is you can think of sigma as coordinate on the base manifold on which the modular transformations act, the upper half plane, and rho transforms like a vector in the tangent space of this manifold. Yeah, it's similar to a thermal CFT defined on upper half plane. You have to think about Carrollian CFT2 as defined on upper half plane and its tangent space. again, you can define the S and T transformations like you do in under the usual PSL2Z. So the Carroll modular group is generated by this S and T transformations, where S takes sigma to -1 over sigma, and rho to rho over sigma square, and T just shifts sigma and keeps rho as it is. And you can compose S and T and generate the whole Carroll modular group. They also satisfy the usual identities, where S squares to identity and ST cube also is identity. Great. So now let's come to Carroll characters. So a bit of representation theory of Carrollian CFTs, Carrollian algebra. So we label the primaries with primaries as the eigenstates of L0 and M0 with the following eigenvalues. So delta is the eigenvalue for L0 and xi is the eigenvalue for M0. And the primary states are such that ln's and m's annihilate all the primaries for n greater than 0. And the generic descendant is thus formed by acting ln's and mn's with negative integers. Very similar to highest weight representations of CFT. But now you have both the L and M. There's another type of representation which are known as induced representations. These are the representations where the super translations or MNs annihilate, all the MNs annihilate the primaries except M0. So generic state is labeled by or obtained by acting on a primary with all kinds of ln's with positive and negative n's. The interesting thing is that the characters turn out to be identical for both these representations. So we don't have to worry about which representation we use. And the characters are given by this formula. It's a bit similar to CFT characters, but there's, for example, there is the square of eta instead of eta. Something like this also happens in warp CFT. And yeah, the numerator is essentially the same. It's not qualitatively different. And for the vacuum, you again have to do this subtraction of null states, which gives you this vector, and you set delta and xi to 0. Great. So now we are able to write the partition function as sum over the characters, just like we did in a CFT. And this D just refers to if there are multiple primaries with the same weight. So yeah, this is essentially what we did in a CFT. Right, let me just summarize what this background of Carrollian CFT2. So two-dimensional QFT, which is invariant under CCAR2 or BMS3 symmetries. It can be obtained as a limit of CFT2. And the thermal, there's a well-defined action of modular transformations on this theory. And the partition function can be expressed in terms of characters. Great. So now we want to ask the same question. Are there any universal sectors, just like the Cardy and near-extremal sectors we found in CFT2? Are there such sectors present in Carroll CFTs? And the answer is yes, there are. And for that, to see that, we'll consider Carroll CFTs with the following two assumptions. We assume positive spectrum for delta and xi. And again, an assumption similar to twist cap, which is that the only primary that has xi is equal to 0 is the vacuum. Now, the modular transformation imply that the partition function is the same in the direct and the modular transform channel. This is the modular S transformation. And the partition function can be written as the sum over characters, as we saw, and the character. So I'm just expanding the right-hand side in terms of characters. Now, what we want for the vacuum to dominate is that all the non-vacuum characters are suppressed as compared to the vacuum characters. And that would mean, like, once this is true, you know that the result that you would get are independent of the spectrum, like of the detailed properties of the spectrum. So they are somewhat universal. That's what we want. And we'll see when is this true. When is the vacuum character dominant? It turns out that there are these two regimes where the vacuum character dominates. The first one is where beta omega is going to 0 from above, and both beta and omega are negative. And the second one is where beta omega square is going to 0 from below, and again beta and omega are negative. There are other interesting regimes which are possible if omega is taken to be purely imaginary. We are still looking at them, but it seems like there are other regimes which are possible. And one thing to note here is that it seems like it is true that the temperature is negative for both of these regimes, which might seem a bit weird, but this is true also in the bulk. So for the flat space cosmologies, also the temperature is negative. And one way to see it is that you can obtain the flat space cosmologies as limit of BTZ. And the horizon of the flat space cosmologies is really the inner horizon of BTZ that becomes the cosmological horizon of flat space cosmologies in the limit. And inner horizons have negative temperature, so flat space cosmologies have negative temperature. So it's not too surprising that we need to take negative temperature for these sectors. Great. So by the way, so the first sector is the well-known Cardy sector, which was known for BMS3 theories. The second one is, what do you mean, sorry? Mm-hmm. So the entropy, so it's a bit like de-Sitter. So when it's like entropy decreases with the, so it's, yeah, energy is probably bounded above, but it's positive. So it, yeah, I'm also not sure, a good way of think. I always think of it in terms of analogy with de-Sitter, where it's like you have a max. No, so it's right, but the entropy decreases. So when you have a black hole there, if you put a black hole in there, the larger the black hole, the entropy decreases. And you could, it's the same statement. You could either say that the temperature is negative and the entropy is increasing, or you could say that entropy is decreasing and temperature is positive. Right? It's just in the first law, it's dE is equal to TdS. So either you make ds negative or you make temperature negative. I'm not sure how would, if there's a problem with the partition function. Yeah, because again, we don't have an explicit example of this theory. We are just looking at it from the like a formal point of view. Like you define a partition function, you assume some assumptions of the spectrum, and just like we did in a CFT. So yeah, it's not entirely clear how one should look at these theories with the negative temperature. But Yeah. I mean, in principle, you don't need a negative temperature. You need a negative temperature if you want this vacuum dominance. If there is such a sector, then we have to take these limits. It might be that it doesn't exist. You might say, okay, there is no, I'm working with positive temperatures, and then such a sector doesn't exist, and it's fine. But yeah, if you want these sectors to exist, then you need, or you allow omega to be imaginary, then you can have positive beta, but then the energy becomes negative. So it's, yeah, not entirely clear. If things are well defined and so on. All right, so maybe just in interest of time, I will. It's a lot of stuff still to go, but okay. Maybe I'll finish after this. And so, yeah, in the Cardy regime, when you take this limit, the partition function is well approximated by this expression. And in the Cardy near-extremal regime, it's the same partition function as Cardy partition function plus times this factor. And again, we see that both have BMS Cardy behavior, which is given by computing entropy from this partition function, but there is something extra in the Cardy near-extremal regime. Which these corrections are again generically small, but they might be important. Now we'll explore these corrections further. So you can take further limit on the on this second sector. And what we do here is that we were already taking beta omega square to 0. We now take beta omega to be very, very large. And then we get a Schwarzian-like partition function. So you see, so if you will take beta omega to be our beta twiddle, then there is this 1 over beta appearing here, 1 over beta twiddle appearing here, and there is 1 over beta twiddle to the power 3 instead of 3 halves. So this is similar to Schwarzian partition function, and instead of 3 halves, you get 3, which is probably due to presence of 6 zero modes instead of 3, because now you have 6 global generators of the vacuum. The isometries of the vacuum, which is M0 plus minus 1 and L0 plus minus 1. Yeah, this is different from 3 zero modes of Schwarzian theory. Right, so let me summarize this part. So generic class of 2D Carroll CFTs seem to have 2 universal sectors, namely Cardy and Cardy near-extremal. Both of them reproduce Cardy entropy, but the Cardy near-extremal regime has a subsector which gives a Schwarzian-like partition function with interesting log corrections. And they require negative Carroll temperatures, which seem to be consistent with bulk results, but yeah, needs to be studied further. The bulk interpretation is also not entirely clear, because since there are no black holes in flat 3D Einstein gravity with lambda is equal to 0, so we don't know what the near extremality would mean in the bulk. Probably, yeah, we don't know the answer. Okay, so shall I stop here, or I mean, there's one more part, but we can skip that. It's about the. Okay. Okay. So yeah, one can obtain the same results from S matrices also. You can essentially get the Schwarzian density of states from modular S matrices. And for CFT, these are known, and one can, this was done by Ghosh, Maxwell, and Toriachi, and one can get the Schwarzian density of states. And yeah, for the Carroll CFTs also, we found the modular S matrices, which are given by this formula. And again, you get something reasonable. You get the density of states going as square root of E. So it's kind of like sine hyperbolic square root of E when E goes to 0. So yeah, so but yeah, it's the same result, but it's not exactly similar, but it's like there's a square root of E. So this PM is essentially going as square root of E. So that's the, yeah, but it's there are some complicated factors that are there. So the only point I'm making here is that as energy goes to 0, the density of states does go to 0, which we want because yes, there's no sine hyperbolic, but there's a square root of E from here. But then there's finite contribution from this guy. And there is, this guy doesn't really contribute. So it's a different behavior, but there's a square root of sitting on here. This one, that's true. Yeah, there's an E to the square root of E. That's true. But this still doesn't, like, I mean, in the E going to 0 limit, it can be expanded as 1 plus something. Yeah, kind of same, but there's this term. Like it's not exactly the same. There's this term. It's going to 0. That's behavior is similar. It's going to 0 as square root of E. That is also true. Yeah.
You should think that it is comes to the fact that your D is square root.
Sorry. Right. No, I understand the confusion. Yeah, so the thing is that one really needs to go to one cannot work in the grand canonical ensemble. So we get this factor of 3 in the grand canonical ensemble. And for example, in the warped theory also, you get a factor of 2 in the grand canonical ensemble. But when you go to this fixed charge ensemble, which is the relevant one, there you get 3 halves again. And here something similar seems to happen. Like if you go to this fixed charge ensemble, fixed angular momentum ensemble, then you again get 3 halves. Maybe it's related to that it's the grand canonical ensemble seems to have different powers when you are, depending on whether you are working with CFT, warped CFT, or Carrollian CFTs. But in the canonical ensemble or the fixed J ensemble, they all seem to have 3 halves. Maybe it's that, but also again, this is still really very preliminary result. And yeah. All right, I'll just summarize now. So we observed that 3 different types of 2D QFTs have universal near-extremal sector, different from the universal Cardy sector. And the common characteristics of these theories was that there was modular symmetry, and there was at least one copy of Virasoro in all of these theories, and we were in 2 dimensions. Now the real question is, since we have this universal behavior in the bulk for all kinds of black holes in all dimensions, so one might expect similar universal behavior for their dual QFTs in all dimensions, and yeah, for all kinds of dual holographic theories. But we do not know, we don't know how this would work. So that's the, I think, an important question. And yeah, as I said, there should be a mechanism for this to happen, because higher dimensional near-extremal black holes also show Schwarzian behavior, and their putative duals are higher dimensional QFTs in general. And this might also be related to presence of Cardy formula in higher dimensions, which has been looked at in the past few years. Yeah, okay. I'll end my talk with this. Yeah.
Why should I? For pure CFTs and near-extremal.
Yeah.
Motivated. How's that interesting?
Like, yeah, it's not clear. Like we seem to get a behavior which is reminiscent of Schwarzian partition function, right? So you could ask maybe what does this correspond to in the bulk, right? But what is this behavior capturing from the bulk point of view? And generically, you would say that, okay, this is capturing some behavior of some near-extremal black holes in low energy regime. But here it's not clear because since there are no black holes, there's just flat space cosmology with one horizon. There's no near extremality, like the two horizons cannot get very close to each other. So, I mean, the usual intuition wouldn't work. That's what I was trying to say. So you could, another way to ask the question is, what does this partition function capture from the bulk point of view? That would be, yeah, I don't know. Shall I stop the recording? Yeah. Sure about that. I think so.
Is this pre-status here?
Essentially, not exactly. I just showed the box. I don't think you can change it from. I think you have to take this Chern-Simons coupling to match it. So it's not just the Chern.
E.